Hello everyone, my name is Mohammad Abdul Hadi and today I'm going to present a paper named Attention is All You Need. This paper was written by Vaswani et al. And was presented in the 31st International Conference on Neural Information Processing Systems. In the first part of the introduction, we discuss the problem that the authors of the paper are trying to solve. One is sequence modeling problems and the other one is transduction problems. Sequence modeling is the task of predicting what word or letter comes next. In sequence modeling, the current output is dependent on the previous input, where the length of the input is not fixed. Some of the practical applications of sequence modeling are auto-completion of the text, parts of speech tagging, sequence, classification, etc. In the left-hand side picture, we explain auto-completion in the context of sequence modeling. In this problem, whenever we type a character, the system tries to predict the next possible character based on the previously typed characters. On the other hand, transductive problems basically refer to the language modeling and machine translation problems in NLP or natural language processing. The intuitive goal of language modeling is to compute the probability of a sentence or a sequence of words or to compute the probability of an upcoming word. On the other hand, machine translation or MT is the task of automatically converting one natural language into the other while preserving the meaning of the input text and producing fluent text in the output language. In the second part of the introduction, we are going to discuss about the available solution to deal with the mentioned problems, what the authors of this paper propose, and why the proposed approach is better. Recurrent models are sequential in nature. These models do not accommodate any parallelization within the training examples, which becomes critical at longer sequence length. To remove the constraint of sequential computation, attention mechanisms have emerged as an integral part of the sequence modeling. For most of the cases, such attention mechanisms are used with a recurrent network. If you feel confused about the terms recurrent models, LSTM, GRU, and attention mechanism, please do not worry about them. We are going to discuss briefly about them in the presentation. In this paper, authors proposed the transformer. This is a model architecture based solely on the attention mechanisms. It is different than previous approaches as it entirely gets rid of the recurrence and convolutions. This model allows for significantly more parallelization and can reach a new state of the art in quality with less resources. As an example, for translation tasks, the transformer can be trained significantly faster than the recurrent or convolutional layers-based architectures. On both English to German and English to French translation tasks, it achieves a new state-of-the-art blue score, 28.4 and 41 respectively. In this slide, we are going to discuss about some background and the related concepts, namely feed-forward neural network and recurrent neural network. Imagine we want to determine if there is a cat in a photo. We can train a feed-forward neural network like in the left-hand side figure of the slide. We can use multiple photos with and without cats. In this network, the information moves in only one direction, that is forward, from the input nodes through the hidden nodes if any, and to the output nodes. There are no cycles or loops in the network. These networks are primarily used for pattern recognition. Conversely, in order to handle sequential data successfully, we need to use recurrent or feedback neural network. It can memorize parts of the inputs and use them to make accurate predictions. These networks are at the heart of speech recognition, translation, and more. We will dive into a bit more detailed explanation but skip the complex equations for brevity. Let's consider the given sequence. Paris is the largest city of blank. It is easy to fill the blank with France. This means that there is information about the last word encoded in the previous elements of the sequence or sentence. This is achieved by looping an output of the network at time t with the input of the network at time t plus 1. These loops allow persistence of information from one time step to the next one. In the left-hand side of the RNN figure, we see a circuit diagram where the black square represents a time delay of a single time step. In the right-hand side of the same figure, we see the same network as an unfolded computational graph where each node is associated with a particular time. Each RNN cell updates the memory vector H by deciding at each time step which information we want to keep, which information is not relevant anymore, and we would like to forget, and which information to add from the new input. The RNN cell also creates an output vector which is tightly related to the current hidden state. There goes the short introduction to RNN. In this slide of the background and related concepts, we are going to dive into the LSTM networks, why do we need it, and how it works. One of the appeals of RNN is the idea that they might be able to connect previous information to the present task. For example, consider a language model trying to predict the next word based on the previous ones. If we are trying to predict the last word in the clouds or in the sky, we don't need any further context. It's obvious that the next word is going to be sky. In such cases where the gap between the relevant information and the place where it's needed is small, RNNs can learn to use the past information. But there are also cases where we need more context. Consider trying to predict the last word. In the text, I grew up in France. In the middle we have some other text, and at last we have I speak fluent French. Recent information suggests that the word is probably the name of a language, but if we want to narrow down which language, we need more context about France from further back. It's entirely possible for the gap between the relevant information and the point where it is needed to become very, very large. Unfortunately, as the gap grows, RNNs become unable to learn to connect the information as in standard RNNs. These repeating modules have a very simple structure, such as a single tanh layer. Now, what can be the solution? The solution is long short-term memory networks, usually just called LSTMs. It is a very special kind of RNN capable of learning long-term dependencies. Remembering information for long periods of time is practically their default behavior, not something they struggle to learn. LSTMs also have this chain-like structure, but their cell has a different structure. Instead of having a single tanh layer, there are actually 4 layers interacting in a very special way. The first step in our LSTM is to decide what information we are going to throw away from the cell state. This decision is made by a sigmoid layer called the forget-get layer. The next step is to decide what new information we are going to store in the cell state. This task is accomplished by a sigmoid layer called the input-get layer that decides which values we will update, and a tanh layer that creates a vector of a new candidate values to be added to the state. Finally, we need to decide what we are going to output. This output will be based on our cell state but will be a filtered version. First, we run a sigmoid layer which decides what parts of the cell state we are going to output. Then we put the cell state through a tanh layer in order to push the values to be between -1 and 1. And then multiply it by the output of the sigmoid gate so that we only output the parts we decided to output. In this slide of the background and the related concepts, we are going to discuss a bit about GRU or Gated Recurrent Unit networks. A slightly more effective variation on the LSTM is the Gated Recurrent Unit. In this slide, we can see that it combines the forget and input gates into a single update gate. It also merges the cell state and the hidden state and makes some other minor changes. The resulting model is pretty simple, and it is simpler than the standard LSTM models, and it has been growing increasingly popular. In order to fully appreciate the transformer's underlying logic, we will go over the basic illustration of conventional encoder and decoder, which consists of 3 parts: encoder, intermediate encoder vector, and decoder. Encoder is a stack of several recurrent units. We can use LSTM or GRU cells for better performance. Here each accepts a single element of the input sequence, collects information for the element, and propagates it forward. In the question answering problem, the input sequence is a collection of all words from the question. Each word of the input sequence is represented as xi, where I is the order of that word. The hidden states hi are computed using the given formula, which represents the result of an ordinary recurrent neural network. Encoder vector is the final hidden state produced from the encoder part of the model. This vector aims to encapsulate the information for all the input elements in order to help the decoder to make accurate predictions. It acts as the initial hidden state of the decoder part of the model. Conventional decoder is a stack of several recurrent units where each predicts an output yt at a time step of t. Each recurrent unit accepts a hidden state from the previous unit and produces an output as well as its own hidden state. In the question answering problem, the output sequence is a collection of all words from the answer. Each word is represented as yi, where I is the order of the word. The power of this model lies in the fact that it can map sequence of different lengths to each other. As we can see, the inputs and the outputs are not correlated and their lengths can differ. In this slide of related concept study, we are going to discuss about what is attention mechanism and what problems can attention mechanism solve. To understand attention and what it can do for us, let's use neural machine translation as an example. Traditional machine translation systems typically rely on complex feature engineering of the text. NMT or neural machine translation systems work a bit differently. Here we map the meaning of a sentence into a fixed length vector, and then based on that vector, we generate a translation. Now in the figure, we can see that the decoder is supposed to generate a translation solely based on the last hidden state output of the encoder. These H3 vector must encode everything we need to know about the source sentence. It is unreasonable to assume that we can encode all information about a long sentence into a single vector and then have the decoder produce a good translation. As we discussed, RNNs are known to have problems dealing with such long-range dependencies. Now, although in theory architectures like LSTM should be able to deal with this kind of problem, but in practice long-range dependencies are still problematic. For examples, researchers have found that reversing the source sequence produces significantly better results because it shortens the path from the decoder to the relevant parts of the encoder. It makes things work better in practice, but it's not a good solution because most translation benchmarks are done on languages like French and German, which are quite similar to English, but there are languages like Japanese, where the last word of a sentence could be strongly connected to the first word of an English translation. In that case, if we reverse it, reversing the input would make things worse. So the attention mechanism prevailed as a feasible alternative where we no longer try to encode the full source sentence into a fixed length vector. Rather, we allow the decoder to attend to different parts of the source sentence at each step of the output generation. Importantly, we let the model learn what to attend to based on the input sentence and what it has produced so far. Here in the top right image, the Y's are translated words produced by the decoder. The X's are our source sentence words. Each decoder output word YT now depends on a weighted combination of all the input states, not just the last state. The A's are weights that define in how much of each input state should be considered for each output. So if A3, 2 is a large number, this would mean that the decoder pays a lot more attention to the second state in the source sentence while producing the third word in the target sentence. The A's are typically normalized to sum to 1. Now that we are caught up with the related concepts, we are going to learn about the model architecture of the transformer. In the left-hand side, we show the model as a black box. In a machine translation application, it would take a sentence in one language as input and output its translation in another. In the right-hand side, we exposed the black box to show the actual transformer. In the next few slides, we are going to demystify the concept of the transformer and different parts of it. From here, we can see that the encoder is in the left-hand side and the decoders are in the right-hand side. Both encoder and decoder are composed of modules that can be stacked on top of each other multiple times, which is described as NX in the figure. We see that the modules consist mainly of multi-head attention and feed-forward layers. The input and outputs target sentences are first embedded into an n-dimensional space since we cannot use strings directly. One slight but important part of the model is the positional encoding of the different words. Since we have no recurrent networks that can remember how sequences are fed into a model, we need to somehow give every word or part of the sequence a relative position. These positions are added to the embedded representation of each word, which is an n-dimensional vector. Please do not worry about the bits and pieces of every part of the transformer. We are going to delve into the details. If we pop open the black box of the transformer, we see an encoding component, a decoding component, and connections between them. The encoding component is a stack of encoders. The decoding component is a stack of decoders of the same number. In this paper, authors stacked 6 encoders on top of each other. There is nothing particular or specific about this number 6. We can definitely experiment with other arrangements. Please note that this is a high-level look and we are going to delve into the details of each of the components of this figure in the next few slides. All the encoders in the transformer are identical in structure, but they do not share mutual weights. Each one of the encoder can be broken down into 2 sublayers. One is the self-attention layer and the other one is the feed-forward neural network. Now we are going to discuss about the purpose of these layers. The encoder's input first flow through a self-attention layer. It helps the encoder to observe other words in the input sentence. The output of this self-attention layer are then fed to a feed-forward neural network. The feed-forward networks with exact same structure is independently applied to each encoder. The decoder has both of these layers, but between them there exists an encoder-decoder attention layer. It helps the decoder to focus on relevant parts of the input sentence. This is pretty similar what attention does in the seek-to-seek models and what we have discussed before. In this slide, we explained what is tensor, why do we need it, and how we are going to incorporate tensors in our architecture. A tensor is basically a container which can store data in n dimensions. Often, tensor used interchangeably with matrix, which is nothing but a 2-dimensional tensor. We can think of tensors as the generalizations of matrices to n-dimensional space. The first step of the transformer model is feeding out input into a word embedding layer. We begin by turning each input into a vector using any embedding algorithm of our choice. Word embeddings are a type of word representation that allows words with similar meaning to have a similar representation. We then incorporate the word embedding with the positional encoding vector to generate the first encoded input, which is also known as the positional input embedding. We are going to discuss about the positional encoding at length in the few next slides. Please note that we apply the embeddings only once in the bottommost encoder. The case that is common to all encoders is that they receive a list of vectors with size of 512. In the bottom encoder, the input would be the word embeddings. For the other encoders in the stack, it would be the output of the previous encoder. Before moving forward, in this slide, we are going to discuss an important part of the transformer, which is the positional encoding. Now, the position and order of the words are essential parts of any language. They define the grammar, the actual semantics of a sentence. Recurrent neural networks, or RNNs, inherently take the order of the word into account. But in case of transformer, its architecture ditched the recurrence mechanism in favor of the multi-hit self-attention mechanism. As each word in a sentence simultaneously flows through the transformer's encoder-decoder stack, the model itself doesn't have any clue about the position or order of each word. So we need a way to incorporate the order of the words into the model. We can add a piece of information to each word about its position in the sentence to give the model some sense of order. We call this piece of information the positional encoding. To address this issue, the transformer adds a positional encoding vector to each of the input word embedding. These vectors follow a specific pattern that the model learns, which helps it determine the position of each word or the distance between different words in a sequence. The intuition here is that adding these values to the embeddings would provide meaningful distances between the embedding vectors. Ideally, the position encoding should satisfy the following criteria. It should be deterministic. It should output a unique encoding for each time step. Distance between any two time steps should be consistent across sentences with different lengths. Our model should generalize to longer sentences without any efforts. In the next slide, we are going to talk about the positional encoding in details. The encoding proposed by the authors is quite simple. It's a d-dimensional vector that contains information about a specific position in a sentence. This encoding is not integrated into the model itself. Instead, the vector is used to equate each word embedding with information about its position in a sentence and the other word's position in the same sentence. In other words, we enhance the model's input to suggest the model about the order of the words. Let T be the desired position in the input sentence, and PT vector will be the corresponding encoding, where D be the encoding dimension. Here F is the function that produces the output vector. The authors chose the function because it would allow the model to easily learn to attend by relative position, since for any fixed offset k, pt t plus k can be represented as a linear function of pt t. As we can see from the function definition, the frequencies are decreasing along the vector dimension, and so it forms a geometric progression from 2 pi to 10,000 into 2 pi on the wavelengths. We can also imagine the positional embedding pt vector as a vector containing pairs of sines and cosine for each frequency, like in the bottom left figure. In the given heat map, each row corresponds to a positional encoding of vector. So the first row would be the vector we would add to the embedding of the first word in the input sentence. Each row contains 64 values here, each with a value between 1 to -1. We have color-coded them so that the pattern is visible. In the next slide, we are going to cover the intuition behind how the combination of sines and cosines could ever represent a position or order of a word in a sentence. The intuition behind positional encoding is quite simple. Suppose we want to represent a number in a binary format. The figure in the left-hand side shows how we can do that. Here we can spot the rate of change between different bits. The least significant bit is alternating on every number. The second least significant bit is alternating in every two numbers, and so on and so forth. But using binary values would be a waste of space in the world of floats. So instead, we can use the float continuous counterparts, which is sinusoidal functions. They are equivalent to alternating bits. Moreover, by decreasing their frequencies over the dimension, we can go from red bits to orange bits, like in the right hand side figure. In this slide, we are going to take a look at the bird's eye view of how multi-headed self-attention works. We are going to explain them down the road. As the model processes each word, self-attention allows it to look at other position in the input sequence or the sentence. The model looks for clues that can help lead to a better encoding for this word. It's almost like RNN maintaining a hidden state to incorporate the previous word's representation with the current one. Intuitively, self-attention is the method that transformer uses to bake the understanding of the other relevant words into the one that we are currently processing. In the given pictures, we are encoding the word it in the encoder number 5. So the second head of the multi-headed attention mechanism was focusing on the word the animal, and as we can see from the second figure is that the third head of the multi-headed attention mechanism was focusing on the word tired, and in the right hand figure we put a representation for the all heads of the multi-headed attention mechanism, where we can see that it is actually focusing on different parts of the input sequence in different head of the multi-headed attention mechanism. In the next few slides, we are going to explain the self-attention in detail. The first step of self-attention is to create 3 vectors from each of the encoder's input vectors. So for each word in each encoder, we create a query vector, a key vector, and a value vector. These vectors are created by multiplying the embedding by 3 matrices, which are WQ, WK, and WV. These 3 matrices, WQ, WK, and WV, were trained during the training process. Please notice that these new vectors that we are generating are smaller in dimension than the embedding vector. In the paper, their dimensionality is 64, while the embedding and the encoder input-output vectors have dimensionality of 512. They don't have to be smaller. This is an architectural choice that we can make to make the computation of the multi-headed attention mostly constant. In this picture, we can see that by multiplying x1 with WQ, we can get Q1, which is the query vector associated with that word thinking. By generating these vectors, we essentially end up creating a query, a key, and a value projection of each word in the input sentence. The second step of the self-attention is to calculate a score. We need to score each word of the input sentence against that particular word that is being processed. The score determines how much focus to place on other parts of the sentence as we encode a word at a certain position. The score is calculated by taking the dot product of the query and the key vector for the particular word we are scoring. The third step is to divide the scores by the square root of the dimension of the key vectors. In our case, the square root of the dimension of the key vector is 8. In the fourth step, we pass the result through a softmax operation to normalize the scores, just so they are all positive and add up to 1. This softmax score determines how much each word will be associated to this particular position. Clearly, the word at this position will have the highest softmax score, but sometimes it is useful to attend to another word that can be relevant to the current word. The fifth step is to multiply each value vector by the softmax score. The intuition here is to stiffen the values of the words we want to focus on and dilute or drown out the irrelevant words. The sixth step is to sum up the weighted value vectors. This produces the output of the self-attention layer at this position. In the actual implementation, however, the calculation is done in matrix form for faster processing. We are going to explore that in the next slide. In the previous slides, the first step was to calculate the query, key, and the value matrices. We do that by packing our embeddings into a matrix X. We then multiply the X by the trained weighted matrices WQ, WK, and WV. Finally, since we are dealing with matrices, we can put the steps 2 to 6 in one formula to calculate the outputs of the self-attention layer. Before jumping into how multi-headed attention works, we need to understand the purpose of the multi-headed attention. This improves the performance of the attention layer in two different ways. First off, it expands the model's ability to focus on different positions. And secondly, it gives the attention layer multiple representation subspaces. It means that with multi-headed attention, we have not only one, but multiple sets of query, key, and weight matrices. The transformer uses 8 different attention heads, so we end up with 8 sets of these matrices for each encoder or decoder. Each of these sets is randomly initialized. Then after training, each set is used to project the input embeddings into different representation subspace. When we do the self-attention calculation we outlined before, just 8 different times with different weight matrices, we end up with 8 different Z matrices. But the feed-forward neural network layer is not expecting 8 matrices, it's only expecting 1 matrix. So we concatenate like this one in the top right figure, then multiply them by another trained weight matrix W0 to get a singular matrix Z for the input of the feed-forward neural network. As we have seen in the previous slide, multi-headed self-attention deals with quite a handful of matrices. So I have prepared this neat visualization for summarizing all the steps. In the first step of encoder 0, we embed each word from the input sentence. Let's call it X. Please bear in mind that in all encoders other than number 0 or the first encoder, we do not need the embedding. For encoder number 1 to encoder number 7, we can directly use the output of the preceding encoder as this encoder's input. After the first step, we multiply X with 3 weight matrices, which were WQ, WK, and WV. Please note that different heads will have different WQ, WK, and WV trained on them, and X needs to be multiplied with each one of them to calculate attention using resulting Q, K, and V matrices. As a result, we end up with 8 different Z matrices. These Z matrices are the output of different heads. But as mentioned before, our feed-forward neural network is not actually expecting 8 matrices. It's actually expecting just 1 matrix. So to produce that 1 matrix, first we concatenate all the 8 Z matrices together and multiply it with an encoder specific weight matrix that was previously trained in the training process and named W0. There is only one W0 or WO weight matrix per encoder, and it is trained jointly with the model. One minor detail in the architecture of the encoder that we need to mention before moving on is that each sublayer in each encoder has a residual connection around it. The residual connection is followed by a self-normalization step. We have broken down the add and normalize step to visualize the vectors and the layer norm operation associated with the self-attention in the right-hand side figure. This also goes for the add and normalize step sublayers of the decoders as well. Now that we have covered most of the concepts of the encoder side, we basically know how the components of the decoder work as well. But let's take a look at how they work together. In essence, the encoder starts by processing the input sequence. The output of the top encoder is then transformed into a set of attention vectors K and V. These are to be used by each decoder in its encoder-decoder attention layer, which helps the decoder focus on appropriate places in the input sequence. But in the decoder, the self-attention layer is only allowed to attend to the earlier positions of the output sequence. This is done by masking future positions, setting them to -infinity before the softmax step in the self-attention calculation. The encoder-decoder attention layer works just like multi-headed self-attention, except it creates the queries matrix from the layer below it and takes the keys and values matrix from the output of the encoder stack. Now at this point, we know that the decoder stack outputs a vector of floats, but how do we turn that into a word? That is the job for the final layer, which is linear layer, which is followed by a softmax layer. The linear layer is a simple fully connected neural network that projects the vector produced by the stack of decoders into a much larger vector called the logits vector. The softmax layer then turns those scores into probabilities. The cell with the highest probability is chosen and the word associated with it is produced at the output of each time step. Now that we have covered the entire forward pass process through a trained transformer, it would be useful to glance over the intuition of the training of the model. During training, an untrained model would go through the exact same forward pass, but since we are training it on a labeled training dataset, we can compare the outputs with the actual correct output. Once we define our output vocabulary, we can use a vector of the same width to indicate each word in our vocabulary like in the figure. In this slide, let's assume that we are training our model. Say it's our first step in the training phase. And in this slide, let's assume that we are training our model. Say it's our first step in the training phase and we are training it on a sample example translating mercy into thanks. What this means is that we want to output to be a probability distribution indicating the word thanks. But since the model is not yet trained, that's unlikely to happen. In the left figure on the top corner, there is the untrained model output where it produces a probability distribution with arbitrary values for each cell or word. Since the model's parameters or let's say weights are all initialized randomly, we can actually expect that. We can compare it with the actual output, then tweak all the weights using backpropagation to make the model's output closer to the actual output. Let's look at the top right figure where the target model outputs are given. We will train our model against this training example for one sample sentence. After training the model for enough time on a large enough dataset, we want the output produced by the probability distributions to look something like the figure at the bottom right. Hopefully, upon training, the model would output the right translation that we expect. Notice that every position gets a little bit of probability even if it is unlikely to be the output of that time step. That's a very useful property of softmax which helps the training process. Now, as the model produces the outputs one at a time, we can assume that the model is selecting the word with the highest probability from the probability distribution and throwing away the rest. This is called greedy encoding. Another way to do it would be to hold on to, say, the top two words, assume I and A for example, then in the next step run the model twice, once assuming that the first output position was the word I and another time assuming that the first output position was the word A, and whichever version produced the less error considering both position number 1 and number 2 is kept. We repeat this for position 2 and position 3 and etc. This method is called the beam search, where in our example beam size was 2 and the top beams is also 2. Let's talk about the result of the transformer architecture. The results were divided into 3 different sections. One is machine translation, another is model variation, and another is English constituency parsing. In this table, we are showing the result for the machine translation. On the WMT 2014 English to German translation task, the big transformer model outperforms the best previously reported models, including the ensembles, by more than 2.0 blue score. It established a new state-of-the-art blue score of 28.4. Training took almost 3.5 days on 8 P100 GPUs. Even the base model surpasses all previously published models and ensembles at a fraction of the training cost of any of the competitive models. On the WMT 2014 English to French translation task, the big transformer model achieves a blue score of 41.0, outperforming all the previously published single models at less than 1/4 of the training cost of the previous state-of-the-art model. To evaluate the importance of different components of the transformer, the researchers have varied the base model in different ways, measuring the change in performance on English to German translation on the development set News Test 2013. They have used beam search as described in the previous section. The result is presented in the given figure of the slide. In rows A, the researchers vary the number of the attention heads and the attention key and value dimensions, keeping the amount of the computation constant. In rows B, we observe that the reducing the attention key size hurts the model quality. This suggests that the dot product cannot actually efficiently determine the compatibility. We further observe in row C and D that, as expected, bigger models are better, and dropout is very helpful in avoiding the overfitting. In row E, instead of the sinusoidal positional encoding, the researchers have experimented with the learned positional embeddings and observed nearly identical results to the base model. To evaluate if the transformer can generalize to other tasks, the researchers performed experiments on English constituency parsing. Constituency parsing is the task of breaking a text into subphrases or constituents. The researchers trained a 4-layer transformer with D model, or dimensionality of input and output vector, as 1024 on the Wall Street Journal, or WSJ, with about 40,000 training sentences. The researchers also trained it in a semi-supervised setting with approximately 17 million sentences. The researchers used a vocabulary of 16,000 tokens for the WSJ only setting and a vocabulary of 32,000 tokens for the semi-supervised setting. The results in the table shows that despite the lack of task-specific tuning, the model performs surprisingly well, yielding the better results than all previously reported models. In contrast to RNN seq-to-seq models, the transformer outperforms the Berkeley parser even when the training only on the WSJ training set with 40,000 sentences. To summarize, in this paper the researchers presented a new model architecture called the transformer, the first sequence transduction model based entirely on attention. To summarize, in this paper researchers presented the transformer. It is the first sequence transduction model which is entirely based on attention. It replaced the recurrent layers with multi-headed self-attention. For translation tasks, the transformer can be trained significantly faster than architectures based on recurrent or convolutional layers on both WMT 2014 English to German and WMT 2014 English to French translation tasks. It achieves a new state-of-the-art. In the former task, Transformer's best model outperforms even all previously reported ensembles. Here I attached the references. Thank you.